Good afternoon, class. My name is Linval Morgan from Group 3, presenting on our project report titled Designing and Implementing a Digital Stopwatch. The objective of our report is to design and implement a digital stopwatch using the NIAS2 assembly language. The stopwatch is to have a six-digit 7-segment LED display, a three push button to control its operation. It can measure the elapsed time in centiseconds starting from 0 and up to 99 minutes. The theory behind this experiment is the NIAS2 processor is an Harvard-based processor which operates on 32-bit instruction, 32-bit register, and 8-bit memory cells. The processor is in instruction set based with 3 general types of instruction. These instruction types are I, J, and R type. The instructions can be manipulated to do calculations in sequential manner, then output the results by rewriting them in a specific register. The NIAS2 device also has a few input-output devices. These devices ranges from keys, LEDs, 7-segment displays, and eternal timers, etc. The processor interacts with the input-output devices by loading from and storing to their assigned memory address binary configurations that could produce the desired results. During this experiment, a cluster of instructions will be called upon to perform the desired calculations and sequence to calculate and display the desired watch information. Stopwatch. Stopwatch can be a circuit displaying the actual time in minutes, hours, and seconds, or a circuit displaying the number of clock pulses. However, in this experiment, the functionality is shown with the program written where the timing functions are controlled by various push buttons on the NIAS2 board. By pressing the first push button, that's push button 3, it starts the timer. The second push button key stops the timer, leaving the elapsed time. The third push button key resets the timer to 0. And I'll now pass over to my fellow groupmate, Joel Richards.
All right, greetings again, class. My name is Joel Richards. I am also a part of Group 3. I'll be continuing from where Mr. Morgan left off. So there are 4 push buttons on the DE2 series board. They're labeled from keys 0 to 3. And they are used in the controlling of the stopwatch in this case. Now, when the push buttons are activated, they represent or they output a high output, meaning a 1. And when they're released, they output a 0. Now, in our case, the 0 key is not used. However, key 1 is used as our reset button. Key 2 is used as our set button, and key 3 is used as our start or resume button. And as you can see in the table, the different binary values that are required for the relevant output based on each key. Now, for the green and red LEDs, there are 18 red LEDs on the DE2115 series board, and these LEDs are stored or have a register that is set at the base address of 0x1000000, and there are also 9 green LEDs that are at base address 0x1000010. Now, the green LEDs in our case are used to indicate which button has been pressed, which push button has been pressed, and the red LEDs are used to track or display the counting of the stopwatch. Now, for a 7-segment display, where there are 2 parallel ports on the board that are attached to the 7-segment displays, and each is 32 bits in size. Now, the registers that are attached to the base addresses drive or control the different hex displays. So for the base address 0x1000020, that base address controls the first 4 hex displays, and the base address at 0x1000030 controls the hex displays from 4 to 7. In this table, you can see the required hexadecimal value that is needed for the corresponding display. So for example, 0x3f produces a hexadecimal display of 0, 0x07 produces a 7 at the hexadecimal display, or the LED 7-segment display, and 0x50 produces a common R, which we use in our reset case.
Good evening, everyone. My name is Rajan Stevens, and I'll be continuing from here. So we're presenting on internal timer. So the DE2-115 media computer includes an internal timer. This internal timer is controlled by a few memory addresses. These memory addresses has a base address of 1002.000 going up to 1002.014 in increments of 4. So now the base address, which is at 1002.000, holds the output signal. So this output signal is called TO, and it's actually at the first bit starting from the least significant bit. Once the timer counts down from its initial value, the output for that bit would become 1. Now, to provide a timer with the initial value, we would actually be using 2 memory addresses. The 2 memory addresses would be 1002.008 and 1002.000C. Now, the memory address ending with 8 would be the low value, and the memory address ending with C would be the high value. So the timer actually accepts this countdown value in sets of 16 bits. So the high 16 bits will be provided to the high section, which is the address ending with 0C, and the lower section would be added to the address ending with 08. Moving on to discussion. The approach taken with this project used an iOS-2 process assembly language on the DE2-115 calculator simulator. We then had to identify the required input and output device base addresses and store them in the register for later use. Once that was completed, the hex display for the stopwatch was given an initial look. And this would be the initial look as shown on the screen. The timer was then introduced to the countdown time by storing the upper and lower X codes for the calculated results, which represented the 100th of a second. This calculated result was 500,000. This was done by identifying how many seconds passed before a clock pulse of the 15 megahertz onboard timer, then determine how many of that pulse is needed to count down to 0.01 seconds. That was calculated by dividing 1.01 by the reciprocal of 50 million. A loop was then designed to check for reset set, then starts in the same order. Once there is an input, the code will branch off to the respective button press. Key 3 is used to start the timer as shown in the image on the screen. Hex display 1 and 3 shows the 100 of second count from 0 to 99. Hex displays 1 to 5 shows the seconds count from 0 to 59, while hex display 67 shows the minutes from 0 to 99. Once there is a set entered by the user, the program will continue to calculate the count in the background while it displays the set value on the hex displays. And if the user was to click reset, the code will basically wipe the registers that stores the hex display values and the count values and start the program all over again.
So moving on to the script. Within the first part of the code, the X code of the decimal digits are stored within a label called X codes. We then assign the variables to specific addresses, and below that, in the other section of the code, we initialize the addresses by loading them to specific registers. In this section of the code, we store the initial display of the timer with zeros from X code starting from X7 to X2. Below that is the clearing count register and memory addresses. Within this section of the code labeled reset clear, we cleared count registers and memory addresses by assigning a 0 value to the registers storing the red LED, centisecond, seconds, and minutes. Loading timer countdown value 500,000. And then afterwards, we moved on to the loop. My group mate will pick up from here.
All right, so I'll continue from this section of the code where the program checks for a button press. So in order for the timer to start running or counting, it has to detect a button press of our start resume. Now here in this loop, the input received from the push buttons is loaded into R2, and that is printed or displayed using the green LEDs. Then the program checks for the reset button, for a reset or press of the reset button. Now the contents of R2 move into R3, and R7 is set as a reference point of 1. So when the button is pressed, it should be a 1. So if R3 and R7 are equal, meaning 1 and 1, then it means a reset button has been pressed. And then the program takes it to the reset module, which then performs that function. A similar process takes place for the stop or set button. When the input is moved into R3, the data is shifted to the left to remove any erroneous or possible erroneous input, and then it is shifted back into place and then compared to the reference to see if the button has indeed been pressed. If it has been pressed, it moves to the set module, and if it hasn't been pressed, then it continues on to check for the start. If the start button, similar process takes place here, and if the start button has been pressed, then it moves to the start module. If it hasn't been pressed, then it goes back to the beginning of the loop and does the checks again. Now, going to the reset module. So here, the reset module, what happens is that once the reset button is pressed, the program moves to this module, or this block of code. And what happens is that the register or the hex display is loaded with the zeros, as was done initially at the beginning of the program. And in addition to that, a 50, which represents the byte that is required to produce an R on the rightmost hex display, is used to produce that R. And then once that is done, the program breaks and moves to the reset clear module, which was discussed previously.
Okay, moving on. So if the user of the program actually indicates that we would like to run the program, they would actually be started here at the start module. So once the start module is initialized, what would happen is we would actually store a 0 inside of the timer, the section that actually produces an input, an output. So once that is stored within the timer, we would then store the configuration that would start and continue the timer. Once that is done, we would then check for an output signal from the timer at this section of the code. And if there's an output signal, we would store that signal in R9. And similarly, we would store that signal in R12. So once the signal is stored in both registers, we load the time count into the red LEDs as well. So moving on, we would start to display the value of the count on the X displays. So what we do first is check to see if the centiseconds have reached 100, and if it has reached 100, we would then break off the sec. But if it's not 100, it would continue and continue the operation to display the contents of R12. So R12 would be calculated, and the X code for the contents of R12 will be determined and sent to the hex display. If the contents of R12 did reach 100 centiseconds, the break would actually be shown here where it has sec. So at sec, we would clear the contents of R12 to 0 and display it on the centisecond stream. Once that is done, we would move on to the seconds, where we would add 1 to the register which represents the seconds. The register that represents the seconds would be R13. Once we've added the 1 to it, we would then do a compare to 60 so we can basically determine if the code needs to break to the minutes module of the code. So if it's not 60, we would then continue to display the seconds. And also the current value of the minutes as well. If it was the case that the seconds did reach 60, we would branch off to minutes. So in the section that represents the minutes, we would then check for check to see if the register that stores the minutes, we would check to see if it's 90. Well, sorry, we would check to see if it's 100. But before that, we would assign 0 to R13, which represents the seconds. So once we have done that, we would display it on the screen that shows the seconds. And as mentioned before, if we check and identify that so if the minutes actually reaches 100, what would happen here is that the code would branch off to a section of the code which would clear the display. So this would clear the registers that are actually storing the values that would be displayed on the hex display. But if that's not the case, the code will continue to calculate the hex codes that should be represented on the hex displays. So moving on, if the user was supposed to click set what would happen here is that we've established the fact that we would need to display an L on the first hex display, and that L would be on the same address that represents the centiseconds. So the L should be here, while the centiseconds will be here. So what we would do is determine what the centisecond is at that point when set is clicked, and we would then assign it to R7. Once that is, we would then assign an L to that address and display it on the screen. So within set, once you click it, immediately it would show the value of the X display once the button is clicked. But what would happen here is that within set, the calculations that happened before in start would continue to occur. This calculation would continue while the display would show the value that the set captured when the button was clicked. So once the calculation is made, once it goes through all the calculations, there are sections, there are instances inside of the code where we would basically branch off to a section, a subsection that would check for part or a set. It continues. So if there is a start or a set, the code would basically branch off to the module that manages that section of the code. Well, or manages the calculation that would be required to perform the operation. But if there isn't a start or a set, it would break back calculation within set and continue to calculate what would normally be on the X display before it halts. And this would continue until the user either clicks start or resets. But there is also a subsection of the code that my colleague Joel would explain a little bit further.
All right, so for this module, the display clear module, whenever the program is in the start module and the stopwatch is running, once it reaches the maximum count points, which is 99 minutes, 59 seconds, and 99 centiseconds, the program jumps to this module, which is the display clear module, and it clears the registers that are used to display the count on the stopwatch display. Once that happens, everything is reset to 0, and this module breaks back to the start loop, which then continues the program where it left off. So when the set module is in operation, a similar operation as previously in the other display clear module is carried out here, except that the calculation or the display or the count is not displayed on the stopwatch. And then this module breaks back to the count calculation for the code to continue while the display is not displaying, or while the display is steady.
So we would then move on to the operation of the stopwatch itself. So as you can see, this is the initial look of the stopwatch while it's running. So if we were to click the button that starts it, which is 3, they would start the count using centiseconds of the seconds they make. So once it's counting, if we were to click on the key that represents the set, which is the key number 2, it would hold the current display on the hex display. But as you can see in the background, it's actually still counting as indicated on the red LED. If we were to go ahead and click on 3, which should resume the watch, the stopwatch, you would actually see that it does this and continues at 51 seconds. So while the stopwatch is in operation, if you were to click the reset, it would then bring the display to straight to 0 while providing you with an R, which indicates reset at the X display, at the X0 display. At the same time, while we were clicking the buttons, you would have noticed that there were green indications on the LEDs. And that was it for our presentation. Thank you.